Let me share my screen. Okay, I think you can see my screen, right? So let me go to this fixed material. Okay, so hi guys, welcome to week 4 of the reinforcement learning course. So today we'll try to cover up whatever is left last week. Okay, so let's see whether we can finish our model based reinforcement learning today. Okay, so there is, I guess, only one algorithm there remaining in that end. Uh, and because I'm here demonstrating at IIT Kharagpur's your research expo, right? So I don't have my graphics pad with me. So I'll take help from some slides and some of my previous notes. Possibly I'll share you the notes too. Okay, so that you can clarify your doubts on that later on. Okay. So yeah, again, reminder, if you haven't set up your Python environment, go set it up so that you can do a hands-on. So this was the part that we have covered till now in the model-based reinforcement learning, right? So model-based means, just for a reminder, model-based means when you have when you have hold of the model, a model of the world. So that means you have access to the and model means I am talking about Markov decision processes. Okay, so where you have a decision also. Okay, so you have hold of the action space, you have hold of the reward matrix and the transition matrix, right? Then you have and also you know the gamma or how far you want to look ahead in future to estimate a state, that you also know that let's say gamma is 0.9. That means we want to look for 1 minus 1 by as 1 minus 1 minus 1 by 1 minus gamma, right? So that means around 10 states. Okay. So all these algorithms assume that you have hold of the world. Now, what we did last time, we covered all these concepts like what is return, what is discount factor, gamma, what is value of a policy, right? So value of a policy, if you can remember, it was how much expected return we can get from a state if we follow a particular policy, right? That was value function. So what is return? That means how much total future reward you will get from a state, right? If you take an expectation of that, that gives you value of that state. Okay. And why the return can change actually? Because because what with different Markov chain rollouts, this returns may be different, right? You might visit different states. So that's why you can expect this return can change at a particular state based on multiple runs. So you get an average or expectation of that. You get a value function, right? Now we can solve for value function with that recurrence relation v is equal to r plus gamma pv. And if we just do a matrix solution of that, right? So v would be I minus gamma p inverse r. That's an exact solution that we did last time. Now, if I know a value of a policy, I can compare two policies by just just comparing the value function, right? Just comparing the norm of the value function that we did last time, if you remember. Now, from an MDP to MRP, we can convert an MDP to an MRP by just specifying the policy, right? So let's say there are n number of total policies possible. Then we can just loop through all the policies and sort them by their value function. And that's how you can convert mm, or basically solve an MDP, right? So that's what we did last time. It's called policy enumeration. And do you remember what was the problem in that case? So just to give you a highlight, what was the code? Yes, this was the initial environment that we had, right? So there is a small environment, 9-state environment of policies of 20, like, 2,62,000 policies, right? And the best policy is that one, the 0, 1, 0, 1, 0, 0, 0, 0 to reach that food. And this was the value function for it, right? For every policy, we plotted the value function, and these were the value functions for the thousand to, I guess, 12,000, thousand, sorry, 1,000 to 1,200 policies, right? So we basically sliced up there between those 2,60,000 to 62,000 policies. We just zoomed into this 10,000, 1,000 to 1,200 policies. And that's how the value function changes. So we are basically doing a brute force, right? We are doing search of, we are basically looping through all possible policies in that environment and estimating it value function. So we went for that exact solution, v is equal to I minus gamma p inverse r, right? And based on that v vector, we get a norm and then sort the policy based on that norm, right? But the problem is this number of policies grows exponentially, right? So if you only increase three more states, right? So last environment solving this small environment in 9 states took around 36 seconds. Okay. Now your a 12-state environment, which is just like a 3-state more, right? Three more state from the previous environment. It took 32 minutes to solve instead of 36 seconds for the 9-state environment. So it's a huge increase in computation, right? And why so? Because the number of policies that are possible is a to the power s. So a is always, action is always 4, right? You can only take 4 action at a state. Like for this case, it is up, down, right, left, right? So you can take 4 action, but if we increase 3 more states, it's actually 4 times 4 times 4 computation, right? So that's the logic. So 4 times 4 times 4 into 36 seconds, it give you an order of 32 minutes. Because 4 times 4 times 4 is 64, right? So 60 seconds mean 1 minute. So that means around 32 minutes, 36 minutes it should come, but because of the acceleration in hardware, it comes around 32 minutes. Okay. So yeah, so that's why we see an exponential increase in computation with this method, right? With this policy enumeration method. So you just evaluate a policy and enumerate over all the policies. That gives you a quadratic increase, or no, sorry, an exponential increase in your computation as you increase the number of states. So now tell me, what would be the solve time for an environment for 13 states? Another into 4, right? So that means 32 minutes into 4. That means around 2 hours. So you see the problem, right? That's the problem with this method. You cannot solve a big environment. Even with one more state, it's like 2 hours. So you have to wait for 2 hours to actually have a solution. Okay. Okay. So that's the problem. If we like, let's say model a, like if we look through all the possible policies and get the value function and sort them out, that's exponentially grows as the number of state grows. Okay. Now there is a improved version of this algorithm which can solve much bigger environments, and that's known as policy improvement. And because I don't have access to my graphics pad today, so I'll take help from some slides and some of my notes. Okay. So possibly share it with you later on. So for example, this is one slide from the Stanford class. Okay, it's from Professor Ima Brunskill. You can check out her web page. It's also there. So what we'll do, yes. So now we are going into control, right? So there is actually two type of algorithms we are talking about. One is evaluation, and second one is control. What do I mean by evaluation? Is when we only want to evaluate. Let's say evaluate means I want to know the value of the particular policy. That's called evaluation. And last time we did v is equal to I minus gamma p inverse r. That's an evaluation algorithm. Okay. Now control is when you try to adjust or identify the policy which is based in an environment. That's known as a control algorithm. Okay. Now the thing that we used last time evaluate all policies and then take the best. That's also a control algorithm, but it takes help from an evaluation algorithm, right? You have to first evaluate the value of a policy, then you have to sort the policy. Now, what we will do next is we try to evaluate our, like we try to take help from an evaluation method as well as try to improve our policy over the last policy. So last time what we did, we list out all the policies, right? We list out all the policies and then we kind of sort them out together, right? Whichever has the best value, we take that one as the best policy. Now that's too much computation wasted actually, right? Even if a policy, even if the next policy is not good, then also we need to evaluate it. That gives us burden of like doing so much computation which goes to waste. So now the logic to improve this is there any way, let's say I start with a random policy, okay? I start with any random policy. Is there any way to improve that policy from the previous one? So if I can ensure that the next policy would always be better than the previous policy, that saves me all those wastage computation, right? So all the cases where the see in this diagram, right? For example, in this diagram, see if I start with this policy, I directly jump to this policy, and I don't have to compute any of these values because all of them are lower than this second policy, right? So let's say I start with this. If I have a way to monotonically improve my policy, then I'll always transition to this peak. I'll skip all these policies which have lower value, and I'll also in the next part I will also skip all these values because all of them are lower than the second policy. So it saves a lot of computation for me, and that's the logic. That's why it's called policy improvement instead of evaluation. Okay, so that's what we will do. Now, there is another evaluation algorithm. Okay, so to evaluate a policy, we can always do v is equal to r plus gamma pv and then take the v this side. So v would be I minus gamma p inverse r. But there is a problem. If the I minus gamma p inverse is not invertible, and there are scenarios when this matrix is not invertible. Okay. So for our consideration for the last week's class, we assume that this matrix is invertible, but it may not be invertible always. Okay. See, in those scenarios, we do an iterative approach. Instead of an exact solution, we do an iterative approach. And the complexity is still, so the complexity for computing inverse is s square. Also for the iterative method, its complexity is s square. So in terms of computation, it's mostly same, but for numerical stability, it's much better. So this inverse computation, sometimes it's numerically unstable. Okay. So even if the inverse is not possible, then also we can find out the value function with this iterative method. What is the iterative method? Until convergence. And what do I mean by convergence is the previous v computation and the current v computation, they're very close. Let's say v t minus 1 minus vt is less than epsilon. Okay, mod of that is less than epsilon. So that's what I mean by convergence. Okay, so basically the value function doesn't change too much until we have this criteria met. What we want to do for every state, you just do a backup. So you just do the recurrence relation multiple times. That's how you imagine it. Okay, so what happens is, um, see, initially you initialize v as 0. So you initialize v to be 0. Okay. Now you do the backup v is equal to r plus gamma pv multiple times until the v converges. This is a dynamic programming approach, and it would be actually better if I had the at the graphics pad to explain. But you can think of it as the values or the dynamic programming values in that value table, right? It gets consolidated from the back to the beginning. So the last state to the first state. So for example, whenever an environment terminates, right? So the next state is always the terminal state. So the next state Vs prime would be Vk minus 1 capital T. And the last terminal state always have a value of 0 because it's ending, right? Ending there. So there is no further reward from that point. So if it has a 0, that means the last state always have a value of 0. Okay. Now this previous state, the last state minus 1, that means S capital T minus 1 would be updated with the current reward plus gamma of probability into 0. So that means in the first iteration, the terminal state minus 1, the previous of the terminal state gets updated. In the second run, the previous of the previous terminal state get updated. That's how you basically consolidate from backwards. So in a trajectory, in a Markov chain, the values get kind of consolidated from backwards to the beginning. So as you basically run this iterative loop, your value function would get consolidated. You run this loop until you get a convergence. So that means your previous value vector and the current value vector has a norm less than some epsilon. Okay, that means you are not changing that much. Your value function doesn't change that much. Okay, so this we will do because it's important. So we'll try to run this algorithm. Okay, and we'll check whether the value is exactly same or how much it is different from the exact solution. Okay, okay, let's do that. Let's take this big environment. It's known as iterative. It's known as actually value iteration. Okay. I hope you can see my screen. Right. We take this large environment. Now let's have a policy. Any policy is right. Let's have this policy stored, and this policy is policy. What does it say? Key error. Oh, sorry. State count. Right. So this is my policy. You can see the policy. It's very random, right? Now we want to evaluate its value. Okay. So a one-step approach would be to use this method, right? V norm, this one. So this is the analytic approach. So what we are doing is the analytic approach that we did last time, right? So what was it? R equal to slice the, so we convert the MRP from the MDP with that policy pi, right? So let's say this is the pi, right? This pi. Let's not show it again, or let's show it again. So this is the policy. Okay. Now we put that pi, get the V pi of all the states with I minus gamma P inverse R, and then do and gamma. We need to also specify gamma, right? Gamma equal to 0.9. Now we get the V norm. Now let's print the V norm. So do tab print V pi, comma V norm. And this is my V pi, comma V norm. And this last one is the V norm, right? So let's do a /n possibly. /n. Yes. So this is the V pi and this is the V norm. Okay. Now this is an analytic approach. It might fail when the inverse is not possible. Okay. So what we will do, we'll do the iterative approach. And we are still evaluating the policy. We haven't yet improved it. So the next algorithm will take advantage of this iterative approach to improve this policy, improve any, let's say I start with a random policy and then improve it over time. So we don't have to compute for all the other like non-improving policies. So what was the algorithm again? Okay, so for initialize value to be 0 for all states, then until you converge, you run this v is equal to r plus gamma pb. That's it. So it's a very easy algorithm. So v old is equal to np dot np dot zeros. See what is the dimension of v? V is a um, vector, right? Wait, r pi is a column, so we need to have a column. So our np dot zeros and the shape would be environment dot state count comma 1. This is the v old, right? And now v new can also initialize v new here, and let's initialize v news to be ones. Okay, this is v new. Now our convergence logic is like this: you do a vector difference, right? So v new minus v old, right? Now here you can do many things. You can do L2 norm, right? You can do max norm, infinite norm, anything. Okay, so let's do L2 norm. If their L2 norm is less than some epsilon, and that's for numerical stability, because floating point number cannot be same, right? Even if you write 2, it might be whenever you check floating point number, whether the previous 2 and the next 2 is same, it might always not say true. Okay, so floating point numbers are not exactly same most of the time. So even if they are same for, let's say, 10 decibel places, like 10 decibel places, right? It might not be same for the 11th one. Okay, so let's like this is a way you can control how much decibel places you want to check for. So let's say I only want to check for 4 decimal places, right? So it will be 0.0001. So if it is less than this, right, that means it's 0.0009 something. That means 4 decimal places it will be same. So I'll stop there. Okay. If their norm is less than this, if it is less than this, then you stop, right? So that means the logic will be greater than. So while this is greater than this 0.0001, you loop. And what do you loop on? You loop on value new is equal to what? Value new is equal to R. So these two you want to still want to get, and because these are static, right? We don't change that. So you can compute it outside. V is equal to R pi plus gamma times gamma PV. So matmal P is what? P is RP and V is your V old. This is important. V old. Okay. Now this gives you a new V new, right? Before that, you need to take a backup of the V new, V old. So wait. How we can back it up? Like this. V old is equal to oh, so you see my point, right? So what I'm trying to do is so V is equal to R plus gamma PV. Want to check for the new to old. What is the this thing? Um, or we actually do this. Wait, V and V old. Let's not take out V old, V new, all those things. Okay, so V is uh, zeros and V old is ones. v minus v old, this stuff. Old, we don't want to. So v is equal to r pi plus gamma v old. Now here we want to back it up. So okay. V old is equal to V. That's how you do it. Okay. So V is zeros, right? So you just put V old to zeros first, and these ones were only one. So just to run it for the first time, right? So V old is equal to V, and then you do the loop. V is equal to R plus gamma PV to the like the same thing. Okay. And you just run it until you get the V. So now you don't have to do this analytic solution anymore, and V norm would be same. Let's write it as V pi. That would be much better. V, v pi, V pi, V pi. Okay. So after you converge, let's see whether it converges quickly or not. Yes, it converges really quickly, right? Now, if I print the V pi and V norm, this is the V pi and V norm, and see it's exactly the this is the analytic solution, right? 465.3060, 465.3058. So it's still very close, right? It's 60 instead of 58. Okay, so that's how you can estimate the value function in an iterative approach, not in an analytic approach. Okay, and this works when there is the inversion is not possible. Okay. Okay. And and how this value function converges, you can actually track it. So we can track the v norm over here, put the values in a list. V norm, right? And then plot the plot lt dot plot values. And this, see, this is how the value function converges. It's a standard curve, right? So it starts with 0, and then it's gradually converges to that 453 or 460, 465 value. And unless it reaches similarity with 4 decimal places, we run the thing, and it ran for, I guess, 100 iterations, 100 or 110 iterations, and then it converges to the value. Okay, which is exactly same as the analytic solution. Okay, now we know that even if the inversion is not possible, we can still compute the value. Okay, now what we can do again, like, with this? Let's see. So now this is the formulas of the Markov decision process, right? So where it is defined from a finite set of states, finite set of action, a dynamics matrix called P, a reward matrix called R, and a discount factor gamma. Okay, and this is the example. Yes. So now, given a policy pi, we can, if we just add MDP plus policy, that gives me an MRP that we discussed last week, that why we can just add a policy and an MDP would be converted to an MRP, because you'll basically take the same route in the as mentioned in the policy. Okay. Okay. Now this one we did. So this is like a Bellman backup. Okay. So you just evaluate a policy by just running the corresponding backups like this from the policy. Okay. It's fine. This is not required, not required. Yes. Now to control, to find out of whether a policy is good or bad, right? Um, so whichever state has the maximum value, right? That is the optimal, like going to those states will be my optimal policy. Okay. So this equation says that whichever states has the best value, going to those states gives me like an optimal policy. Okay. Um, anyway, so these are not that much important. Yes. So the policy search algorithm, we already know that we can search for a best policy from all possible number of deterministic policies. That means a to the power s number of policies. And the problem is the computation grows exponentially. That's why we cannot solve bigger environments. Okay. Now like to count for that inefficiency, like we came up with this policy improvement step. Okay, so this is the overall architect, like overall pseudo code is like this: initialize with some random policy pi, and until the previous policy and the current policy doesn't change, so you improve, right? So until there is no improvement, that while loop means that thing only, until there is no improvement. Okay, update the value. Okay, and from the value update the policy. That's the pseudo code. Okay, now from values, from the value of the like from the value of an environment or a state, can we say what is the best policy in that state, or what should I take? We cannot, right? Because value function doesn't tell me anything about action. It only tells me about whether that state is good or bad, right? So then we came up with another value function, which is known as state action value function, or also known as Q function. Okay. Yes. So this is the logic of the Q function, state action value function of a policy pi. So Q pi SA is equal to RSA plus gamma, and then the next transition, right? Transition following the policy pi. Okay, so earlier we have the same equation, but this SA PSA was actually like placed by the policy itself, right? Now what we are saying, we are including the policy in that recurrence only, where every Q value for a particular action would be like the reward for taking that action in that state plus transitioning to the next state and the value of the next state. We don't care about what are the other subsequent action we are taking next. So we are just caring about the first step. Okay. First step action and then follow the policy, something like this. And this is known as state value state action value function. Okay. Okay. So in physical sense, what does Q function means? So I will take the Q value of a particular action in a state is like this. I take action left and then I follow the policy pi. What is the value I am getting? Now right value would be I take action right and then I follow the policy, right? Then what is my value function? That's the change. So earlier it was like I only follow the policy at every state. Now because I want to evaluate on what action, how much value we are getting, it's like this. In a state is ST, I take action A1 and then follow policy pi, right? Then how much value we are getting? If I take action A2, then QST A2 would be the reward associated with A2 plus then follow the policy pi. So this follow the policy pi is the recurrence of the value function, right? You just take the value function, assuming that I know the value function after that. Okay. And that's how you can compute the Q function. Okay. And see, this is very much similar to the previous recurrence we had, right? V is equal to R plus gamma VV. Only change is we now factored in the actions also. Okay. Now the policy improvement state is something like this. Uh, let's say I know the Q function at some point, right? So what will be my next best greedy policy? Whatever Q value has the maximum value. So if I just take an argmax, that's my based policy, improved policy over my current policy. Let's say my current policy is random. Okay. Now I follow a random policy. After I take a left or after I take a right, I follow the random policy. Now I know that if I take a left, then I follow the random policy, gives me 10. And if I take a right and then follow the random policy, I get a value of 12. So I know that the right one is better, right? That's how I can improve my policy. So that's what exactly we are doing. So in the improvement step, we just follow the argmax of the queue. Whichever action has the maximum queue, we take that one. And it's a greedy update. So still it's not an exploratory behavior. Okay. Exploitation behavior. Still not doing any exploration because we know the entire like the world, right? We know the P function, we know the R matrix, the P matrix. Because of that, it's like a planning algorithm. So assuming that the world is known, we don't have to explore. We can directly plan it. So it's a greedy planning algorithm. And what is the greedy step? Whichever q value has the maximum return or maximum value, that will take at the improvement of current policy. So let's say I start with a random policy. The improved policy would be argmax of that q function at that policy. Okay. Now this policy has improved. And what is the value function associated with it? The max of q. Whichever action I took, that particular q value would be my value, right? Because it's a deterministic thing. It's not like I'll take action 1 with probability 0.5 and action 2 with probability 0.5. No, like, right? It's I'm taking either action 1 or either action 2. So even if I do a probabilistic sum, it will be only the maximum value only. So the maximum value would get the maximum probability sum. So it's like 1 times q 1 plus 0 times q2, something like this. So if I take action 1. So basically, if I taking an argmax in value function, it is equivalent of taking a max. So which a value of I plus 1 would be max of q. Okay. So in physical sense, we are taking the next best policy and the next best value function. Okay. And that's what I told like in the previous figure, right? So if I have a value function like this, I start with a random value function, I directly go to the next best value function. And then I don't have to compute all the other value functions which are like not good, which was actually very much waste in computation for the previous algorithm, right? We have to compute for each and every policy, but here we don't have to do that. Okay. And that's the algorithm. So you just use the, instead of v function, you just use the q function and improve the policy. Okay. Yes, and this is the overall thing, that you just take the argmax of q and then take the argmax of q to be as the v. So we'll do that also, we'll see. And by this we can prove actually. So so because we are moving to the next best policy, we can prove that value of pi1 will be always greater than value of pi2, will be always greater than value of pi3, and all these things. So there's a monotonic improvement of policy. Okay, let's do it. And with this, we hope to solve for larger environments. That's it. So because we are skipping all those like all those unnecessary policies that needs to be evaluated in the previous algorithm, like you see, right, that graph here. All these policies are unnecessary. If I have directly this policy, we don't have to compute for all these unnecessary policies. Now here we will try to skip it. So we basically start with the random policy, update it to a next improved policy, not all these unnecessary policies. Okay, so let's do that. Let's have the bigger environment. It is known as policy improvement. Okay, so we get the bigger environment. We start with the policy which is random. Which policy? Yes, pi. Start with the policy which is random. And what is the convergence logic? Let's see it again. where is it? Here, right? The convergence logic was until the policy doesn't change in subsequent iterations, right? So we start with a random policy, we go until the policy doesn't change. So basically, it stop improving. Okay. Okay. And the Q function and everything is same as always. So it's like we initialize everything with 0. So value is equal to np dot zeros state count comma 1 Q function is equal to np dot, let's have it as zeros initially, and this would be what this would be s times a, and we can actually check it. So our equation would be q is equal to r plus gamma ev. This would be our equation, right? So gamma equation. Now v has a state of s cross 1. P has a shape of s cross a cross s, right? So these two would have a state of s cross 1. Now we have to 1, we have to index it to 0. Actually, not index to 0, colon 0, to take out this s cross, sorry, a s cross a cross 1, right? To have a shape of s cross a, and this R matrix is already s cross a, then this Q matrix would be s cross a. Okay, get the shape idea, right? How the shape should be. Now, environment dot state count, comma, environment dot action size. Yes. So that's how you can have the Q function. Okay. Now let's see the algorithm. Now pi. Pi is this. We have a pi old also. Pi old. Okay. Now let's have the pi old to be random as well, because anyway it's just for the first run. Let's both of them to be random first. Okay. Now we start with this. Now our okay, while we are checking for policies which are integers, right? Are they integer? Let's check. Pi. Yes, these are integers. Now what we can do, we can do pi minus pi old. Okay. And if we if the minimum is not equal to 0, right? That means it's not same. So you just do until it's 0. All of them matches, right? So that's how you can do the match. Or you can directly check for pi is equal to, but that gives you an array. Then you have to do again a mean, right? So what do you do instead? Like minus both the policies and check for the minimum. If the minimum is not 0, right? In that case, it's not same. Okay. So until they are not same, so that means we are checking for until they are not same. First, backup. Or we'll not back up here, let's say. Let's see. पहले ये करते हैं. पहले let's update the queue. Queue value update. Let's try doing it outside first. So np dot maxmul PV, right? So environment dot PSAS, comma V. It gives me a shape of as we expect. So we need to then slice it. All values for the first axis, all values for the second axis, but the zeroth value for the third axis. That gives me exactly what we want. And then we do gamma times this, which gives me the like, multiplied with gamma actually. And then we add it with environment dot RSA matrix. And this gives me the Q table, QSA. Okay. Now, this is how you update the Q to be this. Okay. Now, my so we assume that this current V0 is associated with pi old. Okay. And Q0 is also associated with pi old. And this is just to start a loop. Okay. So random policy which has a value of 0 and a Q value of 0 also. And then this is just to start the loop. Now we get the new Q with what policy, which is pi would be updated at np dot argmax of Q, and your value would be updated as let's do it outside actually. Value equal to np dot max. Let's see what argmax looks like. Argmax of Q over the axis 1, right? So first one is the state axis, second one is the action axis. So you give it gives all these things, all these actions that has the maximum Q value. Okay, and we can check for it. So Q. Oh, we haven't run it yet. Let's say we run it for the first time. Update, right? Now you have a Q value of this. And if I just run the argmax, you see, this is how you get the next policy. And you can check. So this one has the highest value. This one has the highest value. This one has the highest value. This one has the highest value, right? And then this one has the highest value. This one has the highest value. This one has the highest value. Again, these things have highest values. Okay. So this is how you can update this thing, and value would be same, max of Q, which is we have to again do a axis wise thing, right? X is equal to 1 for the axis, and you get an array. Now to keep the dimensions of a column vector, you can pass keep teams true, which keep it as a vector, like as a column vector only, so that we have initially decided that it will be a column vector as per the shapes, right? This S cross 1. So you can pass this, and that's how you do policy improvement. So this next policy pi would be always better than this pi old. Okay. And now before moving to pi, what we can do, we can track the pi old, update it with pi. Okay. So we first update the current like track the old track the old policy and then update the policy. Okay. Okay. So just to start, and then this current policy. Okay, run. And we can also track the value norm as we have done earlier. So values is equal to this, and values dot append, we get the norm. V, right? So we get the norm out of it. Also, we are tracking the best policy. So after this thing completes, our pi and pi old would have the same policy as the optimal policy. Okay. So last time with this environment, with this 12 state environment, it took around 32 minutes. Okay. Now let's see how much time it took now. Is it running or is it stuck somewhere? Let me check. Wait, I'll do an I. I think we have something wrong in the code. 0, 0, 0, 0, 0. Why? Oh, sorry. It's not converging. 5 minus 5 is not equal to this. Mm, oh, okay. It's it's changing. Okay. It's actually going. Um, okay. Let's stop it and let's show you a pretty interesting thing. Phi. It's already an optimal policy. You see this? This is the thing for the algorithm. There's a glitch in the algorithm. Why? Because there can be many policies which give you the same value. So there can be many optimal policies. Okay. So even if the policy change 1 bit or 2 bit, right, in some places, it doesn't impact the value of that policy. So instead of iterating over the value, and you can check. So the policies are going on and on and on, right? But the value have long been converged. So if I see the value, see, see, it's already been converged. Look, quite a long before, right? It's like within 10, 12 steps, it has converged, and since then it haven't improved. But because we are checking the convergence with the policy, right? So for example, here, right? So here, see this state, right? Even if I take it down, that also takes me to the cheese with the same cost, right? So even if I take it down here, that also it takes me to the same thing with the same cost and everything. So there can be these two policies where this is down and this is right, have the same value, but the game can toggle between these policies. Okay, and that's how you know that the policy haven't converged. So this check would be incorrect, and you will basically keep on looping. So a better approach would be to check for the thing that we did last time, right? The value iteration. Take an old copy of the value and then check for the value convergence. So that's what we will doing. We will do. So instead of pi convergence, okay, we check for value convergence. P old, let's say np dot once, state count, comma 1. So you check for V first. You just back up the V in the old and then update the V. Okay. And in the check, you just do the check as we did before. So let's copy this. Instead of this check, we perform. Actually, we can do one thing. We can put these two together and these two together. So you get the problem, right? So with this, because there can be multiple policies which have the same value function. So even if it is toggling, we cannot catch it. Okay. So my value function is not improving, but my policy is toggling with some equivalent policies. So with this approach, it might not always stop looping. Even if the value has converged, it will not stop looping. So rather we can just have the value to check for convergence. Okay. Now if I run and why it is converging till now? Oh, sorry, not V5, V old, V minus V old. And now you should work and done. So it ran for only 142 iterations. So instead of how many? Instead of what was the size of this? Instead of running for uh, 32 minutes with how many policies? I don't know. So it's how many number of policies were there last time? Yeah, this one, right? 16 lakh policies. Instead of running for 16 lakh policies, we ran for only 142 iterations. So that's how efficient it is. Okay, and if I check for the policy, policy 0, it's the correct, it's the optimal policy. And how quickly it converges? It converges really quickly. So with only 142 iterations instead of 16 lakh iteration, it converts. And you see the benefit, right? You see we are skipping all these unnecessary policies. We are just starting with some random policy, then jumping to the next best policy, jumping to the next best policy, jumping to the next policy until no value is improved. Okay, and this is how you can and the optimal Q, the Q function for that is if you just check for Q. Q is also converged. These are the Q values for all the action. And this is the value of the optimal policy V. And the optimal policy pi is this one. Okay. So now this is really quick, right? So we can solve a bigger environment now. So earlier we cannot. Okay. So hello. Can we stop based on V pi's? Yes. Yes, you are correct. So we stop based on V pi now, right? Yes. Okay. So now let's see how big of an environment we can solve with this. We can solve really big environments now. So earlier it was impossible, right? So the 12 state environment we had here, it took around how to confirm if we have reached the maximum. It will saturate, right? So the value would saturate like this. That's what we are confirming. So this termination here is actually checking for until the value that we have converged till 4 decimal places. If it has converged till 4 decimal places and we are not seeing any change in until 4 decimal places, you can stop. So that's an optimal policy. Okay, and this is how it looks in practical. So your value would start really quickly going up, 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 and then it starts saturating. And basically you have a good policy. Okay. So this like, optimizing beyond 4 decimal places has a yes, go ahead.
So here we have not done any exploitation. Means we have not done any explorations also, right, sir? So now it's like I have a policy already. From that, I'm just taking the best action. Again, from that, I'm taking best action. It's going on like that. I am not seeing any. It's like a greedy algorithm where we have just exploited it forever.
Yes, but see, there is a catch. These are model-based algorithms. So we have access to the P dynamics and the R dynamics, right? P and R. So what happens actually, you start, so the dynamic, it's a dynamic programming algorithm, right? This is a dynamic programming call, right? Where V starts with some zero values and Q also starts with some zero values. And as you loop, you update those two values, right? So it's a dynamic programming approach. So what happens actually, you start learning from the last stages. So the last stage Q values first get updated. In the next iteration, the last stage Q values get updated. In the next iteration, the last stage Q values get updated. So it's learned in that way. So it's actually a backup. So you're learning from backwards. Got it?
Okay.
Did you get my point, or did I need to, like, do I need to
Maybe little
explain
bit
it?
can you explain, sir? I am able to little I can understand, but little more explanation
Yes.
I'll
So,
be able to
so
understand.
ex yes. So exploration exploitation is only relevant when you do not know the environment. Okay. But because here we know the environment, what happens is the last state value is always zero, right? So in the first loop, which Q values will be correct? The last state Q values will be correct, right? And
Mm,
the other
yeah.
Q values would not be correct. In the second iteration, the last state Q values will be correct. Got it?
Sir, why you're saying last two times back Q value will be only correct? Why?
No, not only the all the values till the last state will be correct.
So when you say
So
correct means it is a confident value.
converged. It
Mm,
has converged. So that means, see, last state value is zero, right?
mhm.
Right. So last state value, we don't have to learn it. Last state value is always zero. So we don't receive any reward after that, right? Like the S capital T, the terminal state value is always zero, right? Now, see the terminal state t minus 1. So t minus 1 state, I know the value to be 0, right? So this matmul operation would give me 0, right? And I know the R. So in the first iteration, the t minus 1 state Q values will be correct. Other state Q values would not be correct, right? Now, in the next loop, the t minus 2 state Q values would be correct because the V value for that Q minus T state will be correct now.
Mm.
Got it? So it's basically learning from backwards. So as you loop, you basically start consolidating the values from the terminal state to the first state. And because you know this P and R, right? This is possible. You don't have to explore. It's like a planning algorithm. You plan. Okay, so
Okay.
exploitation is already only relevant when you don't know the entire model of the world. So you don't know the P matrix, you don't know the R matrix. That's why you have to explore and see, okay, if I take action this, where I should end up. If I take action this, where I should end up. But here, I already know the all the rewards that are possible for taking that action, all the rewards that are possible, all the transitions that are possible from a state. So there is no point of exploring. We already know everything about the world. That's why it's a model based mechanism. And the this is the dynamic programming algorithm, and this is the dynamic programming part, right? And the table gets consolidated from the terminal state to the first state. So the terminal states get fixed first, then that corrected values get propagated to the, like, the initial phases as we loop. And
Sir, can you just go to the visualization of the environment?
visualization of the environment here, this one.
So you're saying like when I run the first iteration, the cheese and then the one blue arrow above and the red arrow,
Yes, this
those
this
two
will
will
be
get
fixed first,
calculated.
and then all the arrows. Yes, exactly. Get my
Okay.
point. So, okay, so this arrow will be fixed first, then this arrow will be fixed first, then this arrow, like this, until you get to the first one. And we can actually check because there are not too many things, right? So we can actually check. We can just do environment dot show. Let's say we can do after 10 steps, we can show the environment, right? I equal to 0, I plus 1, I modulo 10, and so policy pi. Okay. If I run this, does it? Oh, no, it's already converged. So we have to, yes. So the first environment call is 0, right? Is it showing? I don't know. Close, 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 close. Is it learning anything? Oh, okay. So it actually found the, so let me also print pi, right? It actually found the best policy in the first go only. Mm. And then it physically converts the value for the rest. If I just do a restart. Uh, Sorry, gamma 0.9. See, in the first hit only, it find out the best policy. For the next ones, it's actually trying to convert its value. See, it doesn't change. It doesn't change the policy.
Okay.
Yes. So now it's basically trying to learn the value. That's it.
And one more question, sir. So now you have kept the value as initially once, right, sir? The
Yeah.
np dot ones of for the v.
Yeah, be old,
Yes, sir.
right?
Why, why
It's
why
actually
are we
zero.
setting it to once, sir?
So because we are replacing it with zeros. See, here we are replacing it with zeros. Once because we want to first enter this while loop first. Enter the while loop for the first time. That's what it means. So we cannot mention v and v old to be zeros, right? So we keep old to be ones, then we enter the loop and then set it to 0.
Oh, okay. Okay, sir. Thank you, sir.
Got it? Okay. Okay. So this is how it is. Now with this, you can actually solve a very large environment. So let's try to solve it. Why we're printing I, right? We're printing I. So yes, this is the policy. And this is it. So PLT is not there. Import. Net plot dot by plot PLT. So yes, and that is the way we can adapt the value function quickly. And this is the converge q function for that policy, the optimal policy, converge v function for the policy and the policy. Okay. So now let's try solving with a much larger environment. So let's ask ChatGPT. Write a write a bigger model of the world where agent A can reach the goal G and W represents the walls. Let's see. Yeah, this is a much bigger environment, right? Let's see how it looks. Whether it looks solvable or not. If it is not solvable, then we can have to make some ways to reach that state, right? I don't think it's solvable. It's too many walls. Let's see. Um, environment. So, oh, Play as human. If I run this is the policy. This is the world that GPT generates, right? Is there any? Oh, okay. Now this is solvable, right? We can see a lot of ways to solve it. Let's see whether the algorithm can solve it and how many state it has. Let's see. If we want to solve it with the previous um, state count, right? Previous method, what 75 states. So with the previous method, 9 state was 36 seconds, right? So 36 seconds, uh, second times how many? 4 to the power times 4 to the power 75 minus 9. This is the time it will take. So let's see how much time it will take if I go for the previous approach. This is the this much number of seconds. So how many hours? Oh, so it will take 5.4 into 10 to the power 37 hours to complete with the previous method. So now see what, like, how quickly you can converge with this. Yes, done. And the policy found is this. It's cool, right? So it can see anywhere you just start from anywhere, you can reach to the goal state, right? If you even if you start from here, you can come here, right here, and reach here, right? Even if you start here, it will go this way and reach the goal state. So we can solve it in fraction of seconds. Oh, sorry, not interrupt. You can solve it within fraction of seconds rather than a 5.4 into 10 to the power 37. That is like more than the age of Earth, I think. Okay. Yes, and this is the value function. We ran for around 140 iterations again, and the Q functions are this. It's a huge Q function, right? For 70, and this is the value function, all 75 states. And policy is this. Okay, so it's a very powerful algorithm. It's known as policy improvement, or sometimes it's also known as value iteration. Okay.
Sir,
Would you- yeah.
one question. So if we know the transition dynamics
Mhm.
and reward for state action, then we have solved the RL problem. Like for example, in model
Yes.
free, we have to do
Yes.
only these two.
Yeah,
Okay.
we have to know. So if it is a model free method, that means we don't have access to the transition dynamics and the reward dynamics. Then there are a lot of complexities that come into picture. So then we have to explore. So until you explore this part of the environment, you don't know the dynamics, right? So you don't. So there are actually two methods. One is you model the environment by exploring, and another one is you try to directly explore the policy by interacting with the world. Both interact with the world. One estimates the transition dynamics and the value dynamics. Sorry, transition dynamics and the reward dynamics. Another estimates the directly the policy, the policy. So you see in the next model free algorithms, we will mostly update the policy directly, not estimate the P and R matrices. Okay, and that
Okay.
also is only useful when you have a tabular world. So you can store everything, you can store the transition dynamics and probability dynamics. But in real scenarios like a robot walking or any other scenarios, right? You cannot assume that this transition dynamics is storable. It's not storable. It's the state space is infinitely long, and the action space may also be infinitely long. So you cannot store the state space or the action space or the dynamics. So in that case, neural networks come and all. So this is the you can think of for the first basic ML like RL environment where you know everything, you can solve it. Okay,
Okay.
you can solve it with this
Okay.
algorithm. Yes, and this is known as planning also. Okay, it's a planning algorithm.
Okay.
Okay, so I think this is clear, right? How it's working. And the main thing you have to understand is the values, the Q values or the V values are getting consolidated from the end to the beginning. So the last state, capital T, S capital T gets fixed first, then this previous state gets fixed, then its previous state gets fixed until you go like you come to the state zero. And that's why you are updating it in a iterative fashion. It's just like a dynamic programming algorithm. Okay. So this is where our um, model-based reinforcement learning ends. And now this thing, right? Q value, it's known as this Q is equal to R plus gamma PV, or V is equal to max of R plus gamma PV. If you just combine these two equations together, it's known as a Bellman backup. So let me go back to here, right? These are okay. These are proofs of, yes, this is called a Bellman backup. Okay. So V is equal to R max of Xn RSA plus Q gamma PV that we did. It's known as a Bellman backup. And this is a contraction operator. So what do I mean by contraction? This is okay. This we already did. With this. Yes. So this operator Vs is equal to max of all this is known as a contraction is a Bellman operator or Bellman backup, which is a contraction operator. And by rule, contraction operator does this. Yes, this is the logic of a contraction operator. Okay, so let's say there is an optimal value function called V star. Okay, let's say this V is V, let's say V or V prime is the optimal value function. Okay, now if I apply that operator on both sides of this operator V minus operator V dash, because this is optimal, it will not change. Okay, but because this operator is a contraction operator, that means it will be less than equal to the value, the previous value minus value star. So that means previously the difference was, let's say, 10. So the optimal value function is here, and optimal value function looks, you already know how it looks, right? So let's say this is the optimal value function, right? So what does it say is your distance from the optimal value function always always shortens. So see, you start from here, your distance from the optimal value function always shortens as you keep applying this operator. Okay, that's the proof of convergence here. And this Bellman operator, that max of R plus gamma PV that we did, is actually known as a Bellman operator. Okay, so Bellman like this contraction operators have a property of uh, this, where the V star is the converged value. Okay, then it will certainly converge. That's what this proof does. Okay. Yes. Yes, and the convergence is only guaranteed uh, if the discount factor is less than one. Okay, or you have a like if you have gamma equal to 1, it might not converge. That's the only criteria. Okay, so this where is it? Yes, so this Bellman backup to work, the only criteria of this to be a contraction operator is this gamma less than 1. So if this gamma is less than 1, for example 0.9, then the value function will converge to the optimal value function. Okay, so yeah, so this is it. Let me see how much we covered. Yes, so we do policy evaluation. That is that your dynamic approach thing, right? Where you might not have an exact solution, but you can compute it with a iterative loop. So this one is done. Payment backup, just did it. Value function iteration or policy or value to policy monotonic improvement we did. Yes, and that's the end of model-based classical reinforcement learning. Okay, so let's see how much syllabus we have till now, like have with us till remaining till now. So let's see. Mm, Yes, so these are my RL nodes. Okay, I'll give you access to these possibly later on. Yes. Oh, okay, so zooming. Okay, so this is the overall syllabus. Okay, so if you know the model, so there are two approaches called like value function based approach and then policy based approach. Okay, now if you know the model, you know you know the model, and this is the value function based methods. It's known as value based methods. Okay, now if you know the uh, policy and you know the model, okay, it's a policy based method. Now if you only know the value function and the policy, you don't know the world, then that's a model free method. Okay, and now if you know the policy, the value and the world, that's the model based method that we completed. Okay, now if you know the I guess if you know yes, there is a catch. So if you know the value function and the policy and not the model of the world, okay, so that's known as an actor critic method. Okay, that's there in the deep reinforcement part. But yeah, so that's the entire syllabus. So we completed only this corner, this middle corner where we know everything. We know the model, we know the value function, we know the policy.
Okay.
Okay. So now we'll transition to model free methods when we don't have access to the world, but my world is still tabular. So we can still store the number of states, the number of action in a table. So what is the table? Table is my Q function, right? That's the table. Yes, this is the table, right? It's actually all actions Q value for all the states. So we assume that we still store the values in the same table or in a table, uh, but we don't have access to the P and R matrices. Then how we can learn from that? Okay, that's our next like learning tasks and all. Okay, so any questions till now? Let's try solving
Sir,
another environmental.
here you were saying only value function, right?
Only.
Only value function and model and not policy.
Mm-hmm.
What kind of models are we talking? What kind of setup are we talking?
Q learning. Q learning is a method which is a which only deals with a value function and a model.
But
Okay.
policy is eventually output of the value function
Yes.
only. Means argmax of
Yes.
v
Yes.
state.
But so the thing is, there are two ways we can learn the value function, then estimate a policy from it. Let's say with epsilon greedy or something, right? Or Boltzmann sampling or something. There is another approach by directly optimizing for the policy, which is known as policy gradient. Okay, so there is a approach where you don't like derive policy from Q function or V function. You directly compute for policy. Okay, and
Okay.
that algorithms are known as policy gradients. So it's a separate kind of class of algorithms. Okay, and where is it applicable? Is let's say I want to train for joint torques of a robot so that it can work. Then you see this action space is infinite, right? You can have many possibilities of many different like torques at different joints, right? So it's not tractable in a table. So the action space is infinite. In that case, it it doesn't make sense to actually estimate the Q function, right? Because you cannot store the state as well as you cannot store the actions. So then trying to optimize directly for the action makes sense, or directly for the policy makes sense.
Okay.
Okay. And there are a lot of like very famous algorithms like PPO, DPO, your TRPO, DDPG, all these algorithms, all the modern RL algorithms are policy based, not value. Because in most cases, the action space is also infinite. Action space might not be always finite. So some examples of finite access spaces can be games, right? Where you have, let's say, 18 to 20 actions you can perform, and the state space may be very large. In that case, going for a value-based approach makes sense, right? But if the action space is so large that you cannot store it, then you go for directly policy-based optimizations.
Okay.
Okay.
Yeah. Yes.
Okay. So let's solve a bigger environment. It's a much bigger environment. Let's see how quickly it can solve this. Uh, this is the environment. Wait, where is the cheese? It's so big that it's not actually okay. We have another actually a call when we cannot like when your screen doesn't hold the entire thing, right? You can do environment dot screenshot or take screenshot, I guess. Screen get screenshot. This one.
G is not there in the world, I guess, sir. G
Huh?
letter is not there in the
OG
world.
letter
G.
is A. Let's see check the screenshot first. This is the screenshot. plt.im show me the yes, this is my world. Okay. So let's do one thing. Let's just first close this right side. It's not closed actually. Uh, W. Now it's closed, and this one should be closed also. And this is now okay, right? And let's put the G somewhere. I need to also solve it in my mind. There's some way to reach it. Let's remove this one, or going in that direction. Yes. So let's put the G here. Okay. G. Now this is my environment. Let's try to solve it. And there are 234 states. Okay. So the number of time it will take is will be 240, 234, 234.
Sir, also that is
230.
36 minutes, sir. It's not
Yes.
36 seconds.
It's 36 seconds. With 9 state, it was 36 seconds.
Oh,
9 state, 12 state, it was 32. Like for the 12 state environment, it was 32 minutes.
okay.
Right? Yes. So now it will took 7.6 into 10 to the power 138 hours. So it's more than, I'm pretty sure it's more than the age of Earth. Okay. So you cannot solve it with the previous method. Solved. And this is my, anyway, we cannot show it here. So we have to again use that, yes, this one to show the policy. And the policy is pi, right? And this is my policy. You see, it's accurate. So you go in this path. Let me zoom in. So you go in this path, right, go left, right, down, left, down, down, right, 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 like this. You reach, right? Now, if I start from here, let's see, down, and these are not updated. See? So in that loop, the value functions for these states are not updated. So for these states to get updated, we might want to iterate for longer time. So maybe we can have more values, more this because you're doing a norm, right? So because it's a large vector, it's a 143 dimensional vector. Even if some states are not updated, it might also be within that 4 decimal place. Okay. but most of the things would be fine. For example, let's say we start from here, it can reach, right? We start from here, it can still reach. We start from here, it can, so all these values are updated properly, but some part over here is not updated properly, right? So actually it doesn't update from this side. This entire part is not updated properly. So let's see if we can have more zeros over here, whether it updates. Yes. Okay, how many times it ran? It ran for more. Okay. Mm, no, not still not now. Or actually, oh, got it. Actually, the problem is we are only looking into 10 steps, right? So with 10 steps look ahead, solving this part is impossible. Okay, because you need to take a detour from this side or detour from this side, right? So the best approach would be not to increase this, instead increase the lookups. 9 9, now you are looking for 100 next steps to estimate value, right? Now if I run this, it will solve the environment. Yes, it ran for around for more times, right? 1,000 or something, I guess. Let's see how much. Yes, sorry. It ran for 1,800 episodes, which is 1,800 steps, which is also good, not bad. And the policy it learned, and now we can solve, right? See, if you start from here, it goes down, 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 right? And it takes the detour and reach the step, right? Or if you start from here, it again goes for this detour and then stop here. You start from here, it takes the entire detour and reach the here. Now it's solved, right? So why it was not solved earlier? Because you are looking for lesser number of states. So the policy was for this big of an environment, cannot solve every part of the environment. If you are looking for only 10 steps ahead, you have to look for more steps ahead. Okay, for a more complex environment, the gamma should be more. Got it, right? Guys, any questions on this?
Yes, sir. It's clear, sir. This point.
Okay.
So, but in a practical case where we don't know this transition matrix and also the means if we don't know things like what we are saying, especially if we don't know how many states are there in a model tree case, then
Mm-hmm.
this
No,
llama is like such a challenge too.
yes, it's a challenging thing. So that's why in later in the coming algorithms we will do, right? RL becomes more of an art than a science. So so a researcher who is more experienced with training these algorithms will be much better. Let's say both of the researchers know the same logic, same theory, same algorithms, right? But a researcher who is more experienced in training those algorithms can set those values at a good the algorithms are actually very sensitive to the parameters. So with more experience, you get to know which values would work and which values would not work. And as these algorithms are advancing, we are actually getting rid of this this sensitivity towards parameters quite a lot. So for example, the most advanced RL algorithm we have today, right? This PPO, it's known as proximal policy optimization. It's most of the time any decent initialization of the learning rate and all those things, gamma and everything works. But for a Q learning agent, if you set anything, let's say non like if you set a learning rate too high or if you set a learning rate too off from the desired learning rate, it might not converge. So later on, you'll see setting up these parameters are actually very important. Okay. So what we'll do next, so we have completed the model free method, right? Model based reinforcement. Now we still assume that we have finite number of state space, finite number of action states. Um, and we can still store the Q value in a table, but we don't know the PNR matrix. Now, how we can explore and learn? So let's see if I have to interact in the world and solve it, then how the algorithm looks like. That's the model free reinforcement. And uh, next, after that part is completed, right? We'll see when the action space or the state space grow like very large. Let's say it's so big that training it in a table is not a good way to learn, or it might not be tractable in a table. In that case, you use a neural network to approximate the table itself. Okay, and those are like Q learning and stuff. And the policy gradient is a like a different breed of algorithm, so it doesn't also assume the Markov assumption. So in policy gradient, the algorithm doesn't assume for the Markov assumption, and you know, right? So all these algorithms that we do till now all assume the Markov assumption. So this Q is equal to R plus gamma PV came from the Markov assumption, right? That the next state will be always predictable from the previous state. This P matrix is the PSAS is that Markov assumption, because we can predict the next state transition from the current state and the action, right? But it's only true for the Q learning until we have Q learning. Beyond Q learning, when policy gradients and all those method comes, we might the algorithm might not strictly assume a Markovian world. It may also work for non-Markovian world. And we'll see those like uh, there are proofs on that part. Okay. Oh, where is it freezing? Okay. Any questions?
No, sir, it is clear, sir.
Oh, okay. So I think we can stop today. I'm actually not in my campus. I'm here. I in like research park at Kolkata, demonstrating for this silver jubilee event. Okay, so I don't have access to that graphics pad of mine. So or we can actually do that proof. So I plan to do that your UCB proof, right?
Yeah, sir.
But yeah, that would need that graphics pad. But anyway, so the UCB and all those things, these are actually special case. The bandits algorithm is a special case of this reinforcement learning where you don't interact for multiple steps, rather you interact for one step and the environment terminates. Okay, it's a much simpler version of a full reinforcement learning problem. And because of that, you can do all kinds of proofs and stuff for optimality and all those things. Okay. So for bandits algorithm, a good application is, let's say, drug testing or your ads. So you visit a website, you see some ads, right? If you don't click it, it's over for them. It's something like this. So they learn for which region. So the state is basically your demographics, right? And from interaction data, they try to learn in which demographics I want to show which ad. Okay, and you see they don't get too many interaction, right? They don't like unless the ads are refreshed at a time interval. Mostly the ads are static, right? It gets loaded when the site gets loaded once in a while. So let's say once it load and then it stays there for 10 minutes. So if you don't click it for 10 minutes, that ad company gets runs in loss, right? So in those scenarios, bandits algorithms are most relevant.
Okay.
Okay, and but those are kind of restricted view of the full RL problem. We can do them like we can do the proofs and all later on also. Let's see.
Okay.
Okay. So yeah. So let's conclude for today. Next week we can start with the model free reinforcement, and and we already did the question answer sessions for one like week 1 to week 3, right? So we'll wait for I guess one more week, and until this week 4 and week 5 question answers are out, then we can discuss those problems too.
Okay, sir.
Okay, so I'm stop recording. Stop recording.